All right, so welcome to week 10. We will be elaborating more on the application of graph as a data structure this week. So just to recap a little bit about what we have covered in last week, we have introduced graph as a data structure and two important methods in which we can traverse the graph, breadth first search and also the depth first search. And finally, we've introduced graph as a way to represent precedence. And in particular, I think we introduced a concept of topological ordering and an algorithm called topological sort that can allow us to discover the sequence in which we can execute individual tasks, which are represented by vertices, so that we will never violate the dependency relationship, which is represented by the directed edges. Okay, so I think this week, what we'll be doing is that we're going to use this as a foundation to try to see how we can actually apply graph traversal algorithm that we have introduced from last week to use it for a more general setting where we can search for goal in any arbitrary province. And the second part, we'll be talking about how do we do the generalization of the graph that we have from last week, so that we can actually model the problem where edges now carry different weights, and we will probably address one of the most important questions in graph, which is to find the shortest path. All right, so this is one, I think, entertaining example where we can actually surprisingly use graph and the traversal method in graph to find solution to a puzzle. So this puzzle, I think, is very classical, come from very early days in Russia. The puzzle goes as follows. So we have a farmer. He takes 3 of his produce and also his animals to the market in the hope that he can actually sell the animals and also the produce. So with him, he actually have a goat, he have a wolf, and so he has the cabbage. And when the farmer is around all these 3 entities, everything will be fine. But the problem actually occurred when he is about to cross the river. So his boat is actually very small. It can only carry one of the items or animals. So the question over here is that, I mean, here you can actually see the food chain, right? When the farmer is not around, the wolf will eat the goat, and the goat will eat the cabbage. Okay, so of course, I mean, one of the important goals of the farmers is to bring 3 items and animals all the way to the market. So as a result, he has to be very careful in planning how he's going to cross the river without having any undesirable outcomes that occur along the way. And we like to find a way such that the farmer can safely cross the river with minimum numbers of steps. All right, so we will first see how we can represent this problem as a graph. So over here, you see that, I mean, one of the critical representation over here is the individual nodes or individual vertices over here. Yeah, you see that we use the acronym, we use the initials to represent F for farmer, and W for the wolf, G for the goat, and C for the cabbage. And the line over here represent the river. So initially you can see that farmers together with all the animals and produce, they are at the north side of the river. And every time that the farmer crosses the river, you can see that he can choose to bring one of the produce, which is cabbage, or one of the animals with him, but just one and no more. Okay, so let's see how he can make the choices. So initially, this is everything is at the north side, so he can cross the river alone. But over here, we actually label this vertex in red because if you look at it, if the farmer just crossed the river alone, you see on the northern side, the natural food chain relationship will happen. The wolf will eat the goat, or the goat will eat the cabbage, right? So this is infeasible nodes. We will label it as red, means that you should never choose this particular option. The second option is the farmer to bring the wolf with him in the boat. So they will cross the river to the southern side. But then you see that on the north side, the goat and cabbage are being left alone for themselves. So again, this is something that's infeasible. And again, over here, there's no options where the farmer simply bring the cabbage, but then the wolf will eat the goat. So it turns out that as a first step, the only feasible choice will be for the farmer to actually bring the goat over. Then everybody is safe. Right, so you can continue to build upon this graph. You can see that from this point on, the farmer can travel back, or the farmer can travel back together with the goat. But over here, you see that we actually label this particular vertex in a green hexagon, all right? Because if you look at it, this is exactly the beginning node that we have seen previously. So we do not want to repeat our search. So we simply label this particular option as already sorted, already searched. We're not going to visit this particular node again. All right, so it turns out that the only feasible choice will be the farmer to return to the north side of the river alone. Right, so we can continue doing this particular search. Right, you can see that incrementally you explore more and more potential branches. As you explore to the later part of the steps, they are much more possibility. But along the way, you can also discover there's all the repetition in the state, which you see that whenever we encounter a particular state that we have already visited, we will never want to expand that state to save us from the duplication. And also, of course, if any node is infeasible, which is labeled in red, we are not going to expand it any further. All right, so we can actually do the search all the way, and the final destination or the final goal is the case where all items, including farmers and animals and cabbage, they are safely at the other part of the river. Okay, so you can see clearly after you have reached the destination, you can backtrack and just track where are you coming from all the way to the beginning. And that will be the shortest sequence in which you can actually discover the final goal. Okay, so you can actually directly translate all the ages into actions. That will be the minimum numbers of steps that you will be taking. So one of the methods, again, here we pretty much just execute this particular process verbally. But if you like to put this into a computer program and computationally solve this problem, you can see that the traversal method that we have from the previous page is pretty much the breadth first search, right? Because you see that we are going to look at all the nodes that's reachable with one edge, and also all the nodes or all the vertices that's reachable within 2 edges, and then 3 edges, 4 edges, so on and so forth, until eventually the goal pop up as one of the potential next node that we can visit. So because of that, right, so we will always explore all the possibility with given current numbers of edges, and as a result, the moment that we see the goal, we basically will discover also the shortest sequence in which you can actually reach the final destination, which is the goal. Right, so this is a direct application of the breadth first search in searching for the goal states. Right, so again, here you can see the challenge is really about how you can first use the state to represent the individual node, right? So in this case, you see that the challenge that we have is to represent the description of the problem by using individual node, right? So this node just should contain sufficient information to represent really what is going on in a particular node, right? So this is the first challenge. Once you can come up with a representation for individual node, then you can try to connect individual vertices using edges by saying that, okay, so for each and every state or each and every vertex, you basically try to explore all the possible actions that will lead you to the next state, and all these actions in this case will be treated as one edge, right? And then you continue to do so to build the whole graph, and then you can then execute the appropriate traversal method to look for possible ways where you can reach the final destination. Okay, so this I think this is a direct application of the algorithm that we have introduced from last week. So now the challenge that we like to introduce, the second challenge I'd like to introduce, is the case where individual edges actually take on values, weighted values that's not just 0 or 1. So in previous cases, all our edges just doesn't really come with any scales of importance. Either this edge is here, which is represented by the value of 1, or the edge is not here, which is represented by the value of 0. There's nothing in between, or you cannot just emphasize the importance of particular edge by assigning a higher weightage. So in this particular section, our objective is to generalize this representation. We say that, okay, so for a particular graph, you don't really need to have just 0 and 1 for the weight to be associated with individual edges. Individual edges really have different levels of importance or different costs if you choose to take it, right? So I mean, if you actually have a weight, you can actually more generally represent like a lot of more real-world scenarios, like the road network, or I mean, simply representing the fact that every action that's going out of a particular state or a particular vertex may carry different costs or different weights. All right, so in this case, you can see that because we actually have the weight, we use continuous value to represent the age value. So we cannot just simply use 0 to represent the fact that you don't have any ages anymore. In this case, to generalize to the case where we have weights, every time a pair of vertices which are not connected, the age weight is now being set to be infinity, right? So again, this is the mathematical symbol for infinity to illustrate the fact that, I mean, theoretically speaking, they're connected, but the weight is so high, you will never want to traverse that, right? So that's our modified way in representing the fact that two vertices are not connected. Right, so we use a very similar graph structure. This is exactly the same graph that we had from last week. The only difference over here, if you see it, is that individual ages now counts with weight value, and this weight value are all different. In the case of directed graph, you can even see that, okay, so for example, from A to C and back from C to A, you have these bidirectional ages, and you don't have to assign the same weights to both direction, right? So potentially it can be cheaper to travel from A to C, but when you go back from C to A, you see the height, the weight is much higher than the case where you go from A to C, right? So this is actually a very general structure. With this, you can represent any kind of network architecture. The data structure underneath this particular graph is very similar to before. We still have two ways of storing this information. We can use agency list still, and we can also use agency matrix. But the major addition, of course, is the weight, right? You see that for agency list, we don't simply store the individual vertices that we can connect to. Besides the connection, we also need to store the weight of that particular connection. For example, over here, under the rows A, if you have B and C over here, it basically means that the link going from A to B carries the cost of 0.9, and the age going from A to C carry the weight of 0.1. For agency matrix, it's very similar as before. It's just that instead of 1 or 0, we use a numerical value to represent the weight, like the value over here. But the critical thing over here that's make it very different from before is that all the previous zeros, which is the indication that there's no edges connecting any pair of the vertices, now is being replaced by the sign of infinity to indicate that it's impossible to travel from A to D, for example, on this particular graph. All right, so this is very similar underlying data structure to represent the to store the graph data, but with a slight generalization, so we can store more information. So with this, again, we can answer classical questions where a lot of people ask in either transportation network or even social network, right? So of course, in all these cases, the weights may refer to different things. So you may want to like look for shortest path for different reasons, right? But now over here, I think one thing we do notice is that because there's a weight, right? So we are not looking at numbers of ages anymore, which means that the previous two traversal method, whether or not it's a breadth first search or depth first search, cannot really help us in identifying the shortest path. We need newer method, right? And this newer method is directly applied to cases like routing, right? And I think it's very useful. You can use it in all kinds of transportation planning purposes. All right, so how do we do it, right? So I mean, the method that we will introduce today is called uniform cost search. The major difference is how we keep track of the candidate nodes. In a way, it's actually very similar to the breadth first search, but again, because we're using queues. But over here, you see that because the fact that we actually care about the traversal cost. So it's not first in, first out anymore. Unlike the case of BFS, now is actually the lowest cost will be actually explored the next, right? So priority queue is actually the priority queue that's built on top of the past costs that you have experienced so far, right? So basically the priority is established to be the smaller the better, because we are looking at the cost. And of course, because now this particular graph contains more information, so we will need to store more information in the priority queue. Besides the node label, which is the candidate nodes that we should actually expand, we should also store the past cost that has been experienced so far. And also we have to put in have to store the front nodes, from which particular node that you actually see the priority queue, that you actually see this particular past cost, right, inside the priority queue. So let's try to look at this particular example to see how the UCS work. Right, so this is the pseudocode. We will come back to this later, right? But I think I would prefer to use numerical example to explain how this algorithm work. Right, so this is the table we use to track the execution of UCS. Very similar to the case of the breadth first search BFS. Here you see that we maintain 3 columns. The first column is DQ, the element that we're going to remove from the priority queue for processing. And then after that, as before, for all the nodes that we have not processed yet, we're going to include that node into the priority queue, right? And you can see that this is the expansion from before. Previously, we are only storing the node label because that's the only information we need to know. But you see that in the UCS, we need both the node label, this is first information, but we also need to store the cost that has been experienced so far, and the node that's leading to, with the lowest cost as leading to this current candidate nodes. The first node that we can include is the starting location. Here in this case, we try to find the shortest path from A to F. Right, so the first node that we will include into the priority queue will be A, and we will terminate the moment that we have DQF. That basically means that we have discovered the destination nodes. All right, so we will trace this particular program one node at a time. So you have the first node. So the first step, you have no other choice. You simply DQ A, and again from A, you can look at the agency list. You have B and C. So you will include B and C, right? So over here, you can see that the second value, right? The weight that we come up with 0.9 is actually the cost it takes you to traverse to the previous node, which is A. In this case, it will, because A is the starting node, so the cost to traverse to A is simply 0. So the cost to traverse to B as a result is actually 0 plus 0.9, which is the age cost, right? And for C, of course, this 0.1 is the age cost of C. And for both cases, B and C is the direct next node from A. So we put A as the previous node. So now you have two candidates. Again, it's not first in, first out, or we do not really follow fixed alphabetical order anymore, as in the previous case. To get the next candidate, you see that we look at, for example, the current candidate list, B and C. C has the lower total cost to traverse to, so we pick C as the next node. Here you see that we actually record down what is the previous node that's leading to the node C. From C, you can see that we can go to both A and D, but A has been DQ'd already. For any node that has been DQ'd already, we will not insert it for the second time, because the moment you DQ the node, it means that you have already discovered the shortest distance to traverse to that particular node. All right, so you can see that the DQ'd node, we should always remove that. We only have D left. So you see that we don't have C anymore because C is being DQ'd. But we do have D. Right? Over here, you see that again. Let me highlight a bit how 0.2 is calculated. D is actually coming from C, right? So to calculate this cost to travel to D, we use the cost that you will visit C, which is 0.1, plus the cost of connecting C to D, which is 0.1, right? So it's 0.1 plus 0.1, and that's the result. 0.1, and as a result we have 0.2, right? So again, we try to expand the selection, right? D will be the next one with the lowest cost of 0.2. We record down D is actually coming from C, and from D you can see that we will include both B and F, right? So you can see that B actually appear for the second time. This is allowed because we have not discovered the shortest path to B yet. Right, so which basically means that as long as you have not DQ'd that node, we will continue to explore all the other possibility that you can traverse to that node. Right, so for the new value, you can see that now we actually have a lower value. So let's look at this particular process again to see how we can actually derive 0.4. So 0.4 is actually derived from the fact that the previous node D actually take you 0.2 to traverse to. And then the cost connecting from D to B is 0.2. So 0.2 plus 0.2. That's how you actually derive 0.4. And because this particular cost is actually lower than the previous way of reaching B, you will override B, right? Because again, the reason why you will override the previous B is because this is a priority queue. So if you have the same destination, right? Remember, every node can only be DQ'd one time. And 0.4, because it comes with the lower cost, it will always be DQ'd the first. And once B is being DQ'd, the second instance of B, which taking the cost of 0.9, will never have a chance to be processed. So that's why you can safely delete that once a lower cost alternative emerges. So the second one, again, is a 1. Again, the reason why you have 1 is because the previous cost is 0.2 plus the cost is 0.8, right? To go from D to F, so you have 0.2 plus 0.8, it gives you 1.0, right? So the next node you process will be the one that with lower cost, will be B, right? So you can see that this time, this is the reason why we have to keep track of the previous node that is leading to this particular node, because there are two possibilities, right? So B can be reached through D, or it can be reached directly from A, and these two different options give you different costs, right? And the one that give you the lowest cost, which is 0.4, is actually coming from D. That's why we have to keep track of where you are coming from. So B actually lead to C, D, and E, but C and D has been DQ'd already, so you don't include that for the second time. You only include the node E over here, right? Again, 0.9 is a result of 0.4 plus BE give you 0.4, right? So that gives you 0.9. All right, so the next one, you pick the lower cost, which is 0.91. So E is coming out. You can visit D, but D has been DQ already, so you don't process that. So the last node as a result that you process will be F. So now you can see that this value 1, this is the cost of the shortest path, right? Because it's the lowest possible cost that you will ever be able to reach node F. And now if we want to discover the shortest path, again, it's not the sequence. This is the traversal sequence. If you are interested in the sequence in which nodes are being processed, but this is not the shortest path. To get the shortest path, you have to do the backtracking. So again, over here, let me probably just rewrite the way where you can generate the shortest path from this particular sequence, right? You take the final destination, which is F. From this information, you know that it should be coming from D, right? So D will be the previous node, and you look it up. D occurs over here. D should be coming from C, right? Over here. So C is the previous node, and you look up for C. C should be coming from A. So you continuously backtrack until you have reached the origin, right? And this will be your shortest path, ACDF. Right, so this is basically it, right? So this is called the UCS. And further improvement is actually possible because if you look at it, you ask yourself this question, right? I mean, if you come from SMU, you want to go to NUS, based on UCS, you will gradually try to expand the search range until eventually NUS is being included. But you don't really need, right? I mean, practically speaking, you don't need to really consider any alternative that will bring you to the east part and then going west, right? Because NUS is to the west of SMU. It's really no point of going to the east first, right? But given the UCS, I mean, the reason why it's called uniform cost search is that you will consider all the possibility that's with like equal length to the current origin, right? Which means that all the nodes that's possibly going to the eastern side will also be considered, right? So in a way, it's like almost like a scanning, right? So this, let's say this is SMU, and this is NUS, right? What the UCS will be doing is that you will gradually expand the range, right? Like almost like a circle, right? Eventually, when the circle is large enough to include the NUS, and then NUS as a result will appear in the priority queue. That's the moment, yeah, you will actually consider NUS as a destination node, right? So you can see that all this consideration potentially, right? I mean, they are redundant. Really, you don't really to see it. I mean, if you really are seriously trying to find the shortest path, you can actually just focus on this range only, right? This is only range that contains really the competitive solution, right? So this is a further improvement on the UCS. If you can decide how you can actually prune all this unnecessary exploration away, you can speed up the search by quite a bit. And this method is what we call the A-star algorithm, right? So again, we say that this is optional because this particular part is not going to be covered in the exam. But this will be something that's really nice to know because it's almost identical to UCS, just with some very slight modification, and you can actually make it happen. All right, so for those of you who are interested in coming up really very competitive algorithm that allow you to have better performance in searching for the shortest path, I will refer you to this very nice write-up. It's game programming, as you can see from the title. So it's because A-star search is one algorithm that's very commonly used in designing real-time strategy games. Just imagine that it's almost like you select a unit, and then you right-click on any part of the screen, and then the unit should be moving by following the shortest distance to the place, to the destination that you have just clicked, right? And you want to do it very efficiently, so you have a good real-time performance. That's the reason why A-star is very important in designing computer games, actually, right? So if you're interested in how to learn from that, please refer to this particular website. It's very comprehensive, very practical. You can use it to directly improve your program. Right, so I think for you, please use your own time before you move on to the next video. Please work on this particular graph algorithm exercise first, right? So again, we're going to practice the scene that we have talked about in the previous from the previous lesson. We're going to practice breadth first search, depth first search, and also the uniform cost search. Okay, so the information that you should use is that for breadth first search, depth first search, of course, you don't really care about the weight. Age is the only information that matters, right? But when you move on to UCS, you should then look at the weights. That's along the ages. There are numbers as inside the notes. For this exercise is not, you don't have to use it. Right? It's only applicable if you are executing algorithm, more advanced algorithm like A star. So you will terminate the moment you reach one of the goal. Right? So G1, G2, G3, they are all valid potential goals that you can use. So the moment that you have formally visited that particular goal node inside your algorithm, you will terminate. Okay, so we ask you to produce to identify the goal state that you eventually reach, and also you have to note down the sequence in which you have expanded the state or you have expanded the node.